terms of the notations, in terms of the theory. And this theory that I'm teaching you from chapter 13 will apply to all chapters from here. You're going to learn exactly the terminologies I'm saying now, and the theory behind it will apply to 14, 15, 16, 17. So you get it now, then it makes more sense when you get to continuous probability, chapter 16 onwards. Okay? So here we go. Let's start off with discrete random variable. Let's think about it. What does it mean? Discrete random variable is a type of data, okay? But there are two types here. We've got discrete and continuous, okay? Random just means, okay, so I've got a particular data and it is not sequential. It is something that you pick, like if I close my eyes and I randomly pick someone. Okay, you guys have particular data. If I pick someone,
You're going to pay me first.
yes, I can pay you too. So you would represent a data depending on what I'm looking for. What I'm looking for dictates the kind of data that I need. So if I'm looking for number of males in this classroom, so then I close my eyes and I randomly select, then this particular data, number of males, can you count it? And if you can, then is it a solid number? Okay, so if, in terms of males right now, we can say I've got 1, 2, 3, but I wouldn't say I've got half, a third, a quarter of a male. Yeah? But for example, time, if I were to measure you guys when you're running, if I measured you guys and I randomly chose you and I said do a 100-meter sprint, I'm going to time you, then the time can change. See, maybe Xian would get like 5 seconds, 5.2 seconds.
No way.
Maybe David would get 2.2 seconds now. Okay? And maybe Jun will get 2.1 seconds. So the difference here is it would never be solid where I know it's 2, 2, 2. It would now be 2.1, it could be 2.2, it could be 2.222. And so because of that, the measurement for this, that would be called continuous. So the time or the speed that requires to measure your speed, that's the data I'm measuring, then that's continuous. Discrete, on the other hand, I can count. So t-shirt sizes. Small, medium, large. You don't have small and a half. You don't have small, 0.1. Okay, you got small, medium, large. You got shoe sizes. 10, 10 and a half, 11, 11 and a half. Those are discrete because you can count them. It's very sort of categorized. What is continuous? Continuous would be your weight. Everyone's weight will be slightly different. Everyone's height will be slightly different. Temperature. Temperature on every day will be slightly different. You can't say 13 degrees and only 13. It might be 13.1, it might be 13.12. That's the difference. The measurement between it could be infinite or discrete, which is in a particular order. Yes?
So shoe size is discrete, like foot size.
Yes, which is then the measurement for that or the data that you're measuring would be called length. So foot size or the size of your foot is called measured in your length. So centimeters, meters, that's hence height. Height is measured in length. So centimeters, meters, millimeters, those are all continuous data. And so because they're both different types of data, what you're learning in year 11 and 12, technically just 12, is how do you find the chances of something if the data is different? So easily in this classroom, if I said, how do you, what's the chances of picking someone in this classroom that is female, right? Then you can easily count, well, the number of people in this classroom is currently 13. Okay, out of 13, how many females do we have? We've got 1, 2, 3, 4, 5, 6. So you'd say the chances of getting a female in this classroom is 6 out of 13. So that was easy to do. So that was discrete probability, which is what you're doing first, right? If I asked you to do a probability for continuous, for example, right now, every one of you is going to have a measurement, let's say, in terms of your height. The measurement's going to be different. Now, how do I say, what's the chances of you, the probability of getting someone who's exactly 173.1 centimeters? Okay, because I am 173.1 centimeters, but then what's the chances of that? So would I say 1 out of 13? Or is it 1 out of the total number of the height? Because the height could be 173.12, could be 173.17. So what's the total? Whereas discrete was easy to do because you can count them. You can say there's 13 people here, but I can't count the total number of height or total distance in those values. So in chapter 16 onwards, you will learn how to find the probability for continuous data. But in chapter 13, 14, 15, you're learning how to find probability for discrete data, which is something that you can count. Okay, so here we go. These are the ones I'm trying to give you as an example. Foot size, number of males in the classroom, number of chairs in the lecture theatre. These are things you can count. These are called discrete. Okay? Now, let's do an example. Let's use some notations and use some examples to sort of illustrate what you expect at the end of year, the kind of question and how you lay it out to answer the questions, right? So the first one, it says, let X be the number of heads showing when a fair coin is tossed 3 times. Okay? Now, that capital X, that letter X, is very important because X will determine what are you measuring and what type of data you'll have. And that's going to be very important to the end of year when you're doing your exams. When they say let X be or what X represents or what they're measuring is what you want to look out for. Okay? In our case, we know that X represents number of heads when you're flipping a coin. So that means you already know it's discrete because you can count. You either get heads or tails, you know which one it has to be. And you know that you're flipping 3 times. Okay, so if you had to draw a tree diagram of this scenario, you have first go, you're going to get H tails, second go, you can get H tails or H tails, and then finally you can get H tails, H tails, H tails, and then H tails, right? If you were to write out your sample space, you would say that on all 3 goes, you can potentially have all H's. Or maybe you got 2 H's and then 1 T. Or maybe you got H, T, H. Or maybe you got T, H, H. Okay? Or you might have had T, T, H. Or you might have T, H, T. Or maybe you had T, T, T. Now, logically, what's my total number? Yeah, I know. So here's my question. Instead of me listing it and trying to figure it out, what's the total number of, yes, and how do we know? Because it's the end ones, right? Now, if I had 5 tosses, what's the expectation? How many options should I get? If I had, this is only 3 flips, what if I had 5? 2 to the power of 5, because for every option, or for every coin that I flip, I get 2 options. But then on the second go, for every second option, I get another 2. So what you're really saying is for every lot of 2, I get another group of 2. And so for every group of 2, I get another group of 2. So that's why it's 2 by 2 by 2, which is 2 cubed, gives you 8. Okay, and it's the same thing if you had 5 flips. Then you've got for every group of 2, you get another group of 2. For every group of 2, you get another group of 2. For every group of 2, you get another group of 2. So that's why it's 2 by 2 by 2 by 2, 2 to the power of 5, give you total options. So in this case here, I've got 1, 2, 3, 4, 5, 6, 7. I'm missing 1. Which one am I missing? HTT. Okay, so this is what I'm just trying to list out so that you can see. Wait, sorry. I can, Robert. HTT. Okay? Just to clarify, because when you do it end of the year, if you're trying to do it just within your head, you may miss out. But look at the number of branches. So if I flipped a coin and then I roll a dice, okay, that's 2. And then for every 2, I get groups of 6. So what's my total option there? So if I flip a coin, so heads, tails, and then I roll a dice. What's the total number of options here? Don't know? Not 6 squared. So I flip a coin. I get heads or tails on my first go, and then I roll a dice. So I get 1, 2, 3, 4, 5, or 6. 12. Because for every group of 2, I get 6 of them. Yeah, so that's groups of 6. So for every group of 2, I get groups of 6. Kind of similar to this one. For every group of 2, I get 2 groups of those each. Okay, there's 2 for each one. So here, for every group of 2, I get 6 for each one. So 6 times of this group and 6 of these groups. That's why it's 6 by 2. And that gives you 12 groups. Okay, and they would do that in the exam. So they might say, I flip 2 coins or roll 2 dices and then flip a coin at the end. And so you need to understand that for every 6, you get another 6, 6 groups of 6, and then for every one of those, you get 2. So it'll be 6 by 6 by 2. Okay? That's why I'm trying to illustrate that. Yeah? But that's not what we're trying to do today. We're trying to, actually I shouldn't rub it all out. I'll just rub this one out. Okay, so we've got a picture. We've got all the options on the right-hand side. Now it says, find the probability distribution of X. The question is, what is a probability distribution of X? Now this is just another way of saying, I want you to put this into a table. Okay, I want you to put it into a table. Now, a distribution is kind of like your Cartesian plane where you have X values by y values, right? But a probability distribution of x would just mean you have x-axis, which is your x variable, and your y-axis now represents your probability. Okay, that's called a probability distribution. So when you put out your table, this is what you're expecting. You've got your x, and what is x representing in this case? It says the number of heads that is showing when you flip a coin. So now let's think about it. What are the total possible options when you're flipping a coin? You get 2, okay, so you get either x equals 2, you get 2 h's, but some of the options over here, they don't have 2 h's, you also can have 1 h, or none. That's my possible options here, because I'm focused on getting number of heads. When I flip a coin, I can get no heads. In this particular case, TTT has no h's, okay? Because it depends on the first line, and this is going to be very key when you get to binomial distribution. The x determines what you're looking for. In our case, we're looking for x to be the number of h's, not t's. So h's, I can have 0 h's in my possible options.
3 h's.
Can I? Oh, sorry. Yes, you can have 3 h's, like that. I keep forgetting that we're doing 3. Yes. So you can have 0, 1, 2, 3. These are the total number of h's that you can possibly get. And the 0, 1, 2, 3 represents the scenarios, right? And on the bottom, because we're doing a probability distribution, it's not x by y anymore. It is now x by probability. But there is a notational way we represent it. And this is how they do it in your textbooks. And I want you to get familiar with the notation. So here, this is what they do. They write probability of capital X equals little x. Now let me explain why it looks like that, okay? Capital X represents the capital X here. So they're saying the chances probability, what's the chances of capital X, which is this, equaling to one of those. So if I wanted to find this column here, if I wanted to find probability of when x equals 0, meaning only 0 h's, you would say, or you would write probability of capital X, what is your capital X? Represents number of heads, is equal to 0. That's what the little x represents. Okay, and this is the proper notation on how you would write it. Okay, so this is saying what's the chances when your data that you're looking for has 0 heads. Okay, so to find out the chances, what would this equal to? You've already got all the possible options on this side here.
1 on 8.
1 on 8. Okay, so the chances over here is 1 on 8. Or alternatively, you could do what you've learnt in exercise 13a, multiplying the branches. You see, every time you flip a coin, you've got half a chance, half a chance, half a chance, half a chance, half, half. If you want to find one where it doesn't have any heads, you would say it has to be this branch. And what you would have done is moving every branch, you would times. So half times half times half gives you 1/8, which is exactly what we saw over here. Out of 8 options, the only one with 0 h's is TTT. Okay, so what I've done over here is what you did in year 7 to 10, where you're looking at your sample space and you determine what the chances are. Okay, total number of options and favorable number of outcomes. Yeah, so that's what you did. Now we're also adding on from year 11. We would say it would be probability of getting T for the first go was half times probability of getting T the second go. So not a H, not a H, not a H gives you 1/8. Okay, another way of thinking about what the half here represents is probability of H dash times probability of H dash times probability of H dash, because we don't want H. Okay, so that will be T, 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 and that's why it's half times half times half. Okay, if I asked you to write the probability for 1, okay, for 1, you would now say this is probability of capital X, which is the variable of data you're looking at, is equal to 1. Okay, and now you would look at it, and what's the chance of getting only 1 H? Just looking at my data, 3 out of 8. You can see to get 1 H is HTT. You've got another one down here, that's TTH, and you can have THT. Yeah. Yeah.
Think of the top of the big X.
Yeah.
As how many cakes showing up or tails or whatever it is.
Yeah.
And then like the second bit, the little X, is the probability of getting that that way, like when you write, what's the probability that, yeah, I don't know.
Okay, so when I write 0, I'm only representing which capital X, because capital X could be 0, capital X could be 1, capital X could be 2, and capital X can be 3.
So why don't you sub it into capital X?
Yes, because when I want to ask for greater than or equal to 1, then now it's going to be harder to denote, because then you're going to be writing, it's more of like, if you want to describe, if I wanted to tell you to say, especially if you have two pieces of data, if you just said probability of 3, right? We get it, it just means sub 3 in, but then that's only representing for X. What if I had two datas? What if I had one for X and one for Y? Y represents another set of data. Then now you saying 3 doesn't tell me which one we're talking about. But it makes sense if I did this. If I said probability of X equals 3, and then I said probability of Y equals 3. So now you know that this 3 represents the Y set of data, and this 3 represents the X set of data. That's why it's important when you're talking about chances, you don't only get one data. Most of the time you get different types of data as well. Yeah.
For your probability of Y equals 3.
Yeah.
You know how it says like probability of capital X equals little x? Would be probability of capital Y equals little y?
Perfect, yes.
But then what's the little y?
The little y represents what y equals to, because capital Y would represent a set of data. So maybe let's say it's the chances of getting tails. Okay, so number of tails you observe. If that's what y represents, then you can either observe 0 tails, 1 tail, 2 tails, or 3 tails. So when you say probability of capital Y, what's y equal to? How many tails are you looking for? Then you're going to tell them. You're like, well, y is your tails, y will equal to 1. So that tells me you're finding the chances of getting 1 tails. That's why it's capital Y equals to 1. But that little y represents how many of those observed data that you want. So it all comes back to what does the pronumeral, capital pronumeral represent. So, and then that's going to be very key when you start doing binomial, because the capital letter determines what kind of problem you have. So by the end of this course, you're going to learn 13, 14, 15, 16, 17, and 18. Out of all of them, the key factor is...
Sorry, what? There's chapters you mean?
Yeah, these are
What?
chapters, but you only break it up into two sections. One's called discrete, one's called continuous, and then as subcategories, there will be an example of what a continuous data is, which we call normal distribution, and then you have an example of binomial, which is an example of discrete. So while we're talking about discrete, we'll talk about continuous. Under those two umbrellas, each one has an example of a type of data that you have. So discrete would have binomial, and then continuous will have what we call normal distribution, which is your bell curve. Okay? And then on a separate note, chapter 18 is called sampling, which you guys will have done or will be doing in Spesh. Okay, so sampling. So that's technically the 4 categories that you have there. So it's split into 2, discrete, continuous, binomial for discrete, and you've got normal for continuous, and then all those theories combine to become sampling. Okay, so sampling distribution versus binomial distribution versus normal distribution. Okay, so right now you're just learning discrete. Yeah, I know. So discrete, and you got binomial. Okay, so before you get to binomial, you have to really get familiar with this set of notation here. So when you're using it at end of year, how they describe it, they'll be using that capital X, and the capital X will really determine which one you got to solve. Okay, but once you get that across your head, it's very easy to determine, because once you know, easy to do, very easy to do. Okay, all right. So now I'm going to fill out the table in terms of the probabilities. Okay, so now we know how to find the probabilities. I've got the tree diagram on the right, and each one I now know I'm finding the probability of each one, right? We found out this was 1/8, this was 3/8, okay? And then to get 2 H's, you can see that it was either HHT, HTH, or THH. Okay, so that's again another 3 out of 8. Now, if you think about it, that was 1 out of 8, 3 out of 8, 3 out of 8. That's 7 out of 8. So what's the chance of getting all H's? 1 out of 8. Which makes sense, because if you add all the probabilities together, what does it equal to? 1. Which makes sense, because if I asked you to flip a coin and I said, what's the chances of me getting every possible option? It's 100%. because I said every possible option. If I said, what's the chance of me getting every one of these lists here? And you're like, well, if you flip the coin 3 times, you're going to get one of these. I'm like, yeah, I know. Any of these, yeah, any one of these. So therefore, it's 100%. Which makes sense, because if I add them all, it has to equal to 1. And this is so key, because end of year, sometimes you get an easy probability question in exam 1, and all they want you to do is they'll do something like this. They'll do like that. Okay? And they'll say, find P. And some students will have no idea what they're doing just because of the notation. But if I asked you to find P right now, yeah, it won't be hard because you know they all have to add up to 1. And you can create an equation to solve. Yeah? So they'll use fractions and they sometimes put in a square. So they might do 1/8 of P here. And then you just got to figure out what P is. But you just have to understand that if I add all the probabilities together, they have to equal to 1. I get a 100% chance of getting everything. That's what you need to understand there. Okay? So that's what, I'll just quickly flip back to your PDF, chapter 13. It's not that 13. It is this 13. And I'll just show you what they're really trying to describe right... Actually, that's C. Actually, I meant that's D. C is that C? Yeah, that's C. What I just described just now to you is that notation right here. All they're trying to tell you, and this confusing notation, is they're saying for any discrete probability function, because it's a function now where the y-axis is your probability, the x-axis is your data, okay? Then the sum from 0 to 1 of your p function, the range has to be from 0 to 1. Because your probability is either 0% or 100%. And if you sum all of the values together, it should equal to 1. Okay, so you sum all the probabilities together for every x data, that's equal to 1. That's all they're trying to say here. Okay? So don't get confused by notation, they're just trying to tell you what I described on a logical basis. Okay? Now, let's go back to this. So I've got my distribution table. They said show all the probabilities sum to 1. So if you add them all together, it should equal to 1. Now, let's do second part. So if this is A, you got a table. B, find the probability that 1 or more heads show. So in this case here, I'm more interested in notation at the moment, okay? Because I know you can all figure it out by looking at the options, but I want you to figure out how to write it as a notation. Now, probability, we use capital PR, brackets. Now, how do I say that I have 1 or more heads to show? What would you have to write in the brackets now? Good. Capital X is greater than or equal to 1 because it said 1 or more. And capital X represents the number of times you find H. Yes? Yes. Yes, you can. Yes, you can. I'm just thinking sometimes the exams do that. They'll say bigger than 0 and you're meant to pick up that because it's discrete. You can't have between 0 and 1. So you can only have it or you don't. And because of that, you're meant to know greater than 0 actually means 1 or more. That's the difference between discrete and continuous. Because if it was a continuous data, then you saying greater than 0 is very different from x greater than or equal to 1. But in our case, because it's discrete, what you said is correct. Yeah, this would be equivalent to saying probability of x greater than 0. That would be the same because it's discrete. Only because it's discrete. If it's not discrete, saying that would be different. Yeah. Okay. All right. So now, how do we calculate that? So chances of getting H or number of heads that is greater than or equal to 1. How would I solve this scenario? There are 2 scenarios I'm thinking of. 2 scenarios. Give me one. One scenario. What's the answer? How do I find that? I want 1H or more. Yes, Trent? We're all really close here. There's a point why we wrote the table. There's a point on using the table. Yes, Darja? Yeah. Add what up, though? Yeah, because we already know the chances of getting 1 was 3/8. Chance of getting 2, 3/8. Chance of getting 3 H's, again, 1/8. So if I want to know probability of 1 or more, this is the same thing as saying probability of getting 1 plus probability of getting 2 plus probability of getting 3. That's 1 or more. So if you add it all together, that was just 3/8 plus 3/8 plus 1/8, which gives you the answer as 7/8, which you could tell from looking at the data on the right-hand side. You could count which ones will give you 1 or more. Yeah, and out of 8, there's only one that doesn't have a H, which is TTT. Yeah? Now, what's the second option? Very good. This is the one where a lot of students will miss out on. Sometimes when you find end of year, doing this method logically makes sense, but sometimes it takes longer to do because you have to calculate each one. And sometimes not as easy as the one we've just got, where you can just know, oh yeah, 1 is 3/8, 2 is 3/8, 3 is 1/8. It's sometimes much easier if you had done it the other way around, where you said that total has to be 1, which is 100% for everything, minus the chances of not getting what you want. In this case here, it's when x equals to 0, which is really, you're trying to find the complement of that. So if x was to get h's, then what if I don't get h? The only way not to get h is when x equals 0. This would be easier because it's 1 minus, and we know the chances of getting x equals 0 is 1/8 from this side here. Okay? And so 1 minus 1/8 is 7/8. This, you'll find that when you're doing the exam papers, this is generally an approach that you want to start thinking about. And you know by looking at the number of marks. If it's 1 mark, normally it shouldn't take too many steps. Usually, if you're using this step, it's a 2-mark step, because you'd have to find each one, and it takes time. You could be timesing the branches a couple of times before you get this answer, so it's a 2-mark process. If it's a 1 mark, try to see if you can find this answer. Okay? Now, the reason why we call it a probability distribution is you can also sketch this now. So if you were to sketch this table, which I don't know where to roll, I'm just going to move to the next slide. If you were to sketch the table, this represents chances of x. Your x-axis represents your data. In our case, we can have 0, 1, 2, 3, in the H case before. Then you would plot them according to the data. So it could be like this. It'll be something like that. Okay, you get your point. So for what's the chance of getting 1? We said 1/8. Chance of getting 2 was 3/8. So it should have been up here, 3/8. And then it goes down. Okay? I've drawn it wrong, but what I'm trying to show to you is you're going to be analyzing in binomial distribution what a distribution means. So if you have a table, that means you can plot it as well. Okay? And in discrete and continuous, the reason why the graphs are going to be different is that discrete is only in 1 point. They're like scatter plots. In continuous, because between 0 and 1, you can have 0.1, 0.2, 0.21, 0.22, the graph will be like that. And this is going to be interesting because then how do you find the probability of that section? And it works to do the area under the curve, integration. So you find that when you get to continuous, we're using integration. Okay? But let's ignore that for now. Let's go back to this problem. Actually, did I answer the other question? C, find the probability of more than one, hence show. Yeah, that's just greater than 1. So the difference between B and C, one says greater than or equal to, and this one just means more than. So that means you'll be writing probability of x greater than 1, which in our case would be half, as Xian just said. 3/8 plus 1/8 gives you 4/8, which is half. Okay? Let's go to this one now. I'm interested in this one because it ties back what you've learnt about conditional probability, and you've got your independence. Well, in this case, it should be an independent. Actually, I don't know if it's an independent event or not. Let's work with this one. They've gave you a distribution table. So this is your x data. This is your probability of x data. Okay? Now, yes, that's because they wrote it as a function. Normally, you should be writing it as probability of capital X equals little x, providing that this is capital X. Okay? But in each case, you've got x and you've got a function. Okay, now let's answer this question here. First one's going to be pretty straightforward. How do you find the chances of capital X greater than or equal to 4? What is this asking? Good, adding 4 onwards. In this case, X represents the number of chocolate chips in a certain brand of biscuits. So you can either have 2, 3, 4, 5, 6, or 7 chocolate chips. Okay? So in this case here, what's the chance of getting 4 or more chocolate chips in each brand? Now this is what we're going to do. Probability of X greater than or equal to 4. We know this is equal to probability of 4 plus probability of 5 plus probability of 6 and so on. 7 equals to 0.4 plus 0.3 plus 0.02 plus 0.02, which gives you a total answer of 0.74. Good. So A was easy. Let's do B. What was the rule again, or just thinking logically? This now says, what's the chances? So probability of getting 4 or more chocolates, okay, more choc chips, sorry. 4 or more choc chips, given that you already got more than 2. Is it the same? You can't have 2. It said more than 2. So, because it says here greater than 2. Now I don't want just 2, I want more than 2. So if they what they're saying is, what's the chances of getting 4, 5, 6, 7 choc chips if I already know that I got 3, 4, 5, 6, 7? Because they said greater than 2. If I have greater than 2 choc chips, okay? Because they already said, this is the condition. Remember, conditional probability, it's not out of all the choc chips. It's out of whatever the condition is. The condition says, I want more than 2 choc chips. So how do I have more than 2? It's not 2. Because having 2 means that I have exactly 2. It's not more than 2. 3 is more than 2. 4 is more than 2. 5 is more than 2. 6 is more than 2. 7 is more than 2. So when you say, given that you already got more than 2, it's out of this sample. Not out of this total sample. It's out of this sample here. Okay? So how do you find the total sample or the probability? Remember, with conditional probability from C, you would write this as this. Probability of X greater than or equal to 4, given that X is greater than 2, is equal to, what's the chances of X greater than or equal to 4 intersect with X greater than 2, over the chances of the condition. And the condition is greater than 2. Now we already know that the chances greater than 2 were either between 3, 4, 5, 6, and 7. So the probability of that happening is 0.25 plus 0.4 plus 0.3 plus 0.02 plus 0.02. So that gives you what? 99. Okay, so out of the chances of getting more than 2 choc chips is 0.99. Now the question is, what's the chances of getting greater than 4 or more, intersecting greater than 2? So where do they both have in common? Greater than 2 is 3, 4, 5, 6, 7, and 4 or more is 4, 5, 6, 7. So where do they both intersect? Where do they both occur at the same time?
4, 5, 6, 7.
Yeah, 4, 5, 6, 7. That's where they both have the same intersect. That's where they intersect. So in terms of the Venn diagram, when you try to picture the Venn diagram, this is the only time. So that would be, as you said, you found out over here that was 0.74. So your answer now is 0.74 out of 0.99 as opposed to 0.74 out of 1. Okay, that's the difference between the first 2 questions. One is asking getting 4 or more. The second one is saying 4 or more given a condition. Okay? So and then you type that in your calculator, and then you never leave your answers in decimals in a fraction form. You have to divide that on your CAS and get the decimals. And they normally in your exams will tell you how many decimal places you should take. Is it?
Yeah. Whenever you divide by like 9 or 9.
7.
Oh, okay, yeah. Well, they normally would tell you, yeah, they would tell you to round it off by 4 decimal places or 2. And you answer according to what they say. Okay? Last one. Now that you know how to do B, how would you do C then?
Yes. 0.0455. So 9.
Intersection.
X is less than 5.
Good.
Less than 5.
Probability of X less than 5, whoops, intersect with
Given that X is greater than 2.
Good.
So greater than 2 would be 0.25 all the way that way.
Yeah, I'm going to highlight it. I'm going to highlight it. So less than 5 is all the way this way, yes?
Yeah. And then greater than 2 is from 3 onwards. So
From 3 onwards.
At 0.25 and 0.4.
Good. Just those two sections are the only parts that they intersect. So therefore, the chances are, if we write out our answers now, the chances has to be 0.25 plus 0.4, out of which we already figured out greater than 2 was 0.99, and that gives you what? 0.65 over 0.99. Type in your calculator, round to whatever decimal places they tell you. In this case, they didn't say, but normally they do. Normally in an exam, they have to give you a decimal place, and it usually is 4 digits. Okay, so that's why it's important in your CAS. Make sure that your float settings will accommodate for whatever they're going to tell you to do. Okay, because every decimal point will count at the end of year. All right, how do we feel with that? Does that make a bit more sense? But what I wanted you to take out of this session was not how to do those questions, but it was more about notation. So reading the notation and then understanding what discrete probability is and what notation, discrete probability is, and a distribution. Okay, so those are the 3 things I wanted you to take out of 13C, because what you're going to learn from 13C is going to be applied to 14, 15, 16, 17, 18. We're going to use the same symbols, notations. We're going to use the same theory for whatever scenario we're getting. In our case right now, we're dealing with discrete. Okay, and you can tell it's discrete when you can count them. All right, there we go. I'll leave it there. And this is for the next exercise, actually. Expected value. Yeah, second session. Yeah. So I'll leave it. I'll give you guys about 50 minutes. Have a go with exercise 13C, which I'll go to the exercise here. Where's 13C? There we go. 13C. Remember, study smart, don't study hard. Try to look at these questions. Your goal is to understand those 3 things I just said. Read a distribution, understand the notation, and know what discrete probability is or what the variable means. Okay? So the first few questions just getting you to understand what is a discrete variable. Move on, start doing the questions, yeah? So I'm going to stop the video.